optimization problems are some of the nicest calculus application things that you can do. And there are so many areas of business where efficiency and optimization is so important. One of my first jobs, and I might have told some of you this story, one of my first jobs on my first day of work, I was working for a water company, and all we did all day was fill water bottles, the big 18.9 liter jugs, and put lids on them, or small 500 ml bottles or 1 liter bottles, and just fill them up, put the cap on, put them into a box. So we were filling up smaller bottles and we're putting them in a box, and I put them in the box, and I put 12 in a box. And they said, no, we put 10 in the box. And I said, that doesn't make sense. To me, it didn't make sense, because I thought, well, if you put 12 in the box, then you don't have to use as many boxes, it takes up less space, it's going to be like optimization. You could do so much, you can sell more at once, you can pack more at once, it seemed better. Nope, we only put 10 in the box. So later that day I went to my new boss and I said, so why don't you put 12 in the box? Why do you put only 10 in the box? He said, well, 12 doesn't fit. I said, yeah, it does. I put 12 in the box, and the box was like this, and they currently could fit 5 across, and this is what they did, which fit tight this way, pretty good, but left a lot of space up here. So I showed him, well, if you put 4 and then offset them, then you'd get rid of this space and you'd get 12. And so he said, well, that's great, you get a raise. I said, you haven't told me how much you're paying me yet. So I don't know if I actually got a raise that day. He said I got a raise, but he hadn't told me my wage yet, so he could have just lied to me. But apparently I got a raise on my first day of work for figuring out that you could fit 12 in the box instead of 10. But there's a lot of things where optimization becomes really important in businesses. Because if you can save money by doing something and optimize your profits, that can mean huge things, right? If you could figure out for Coca-Cola a way for them to save 1 cent per manufacturer of a bottle of Coca-Cola, think how much money that would save them. I mean, it's 1 cent, it's not very much, but how many bottles of Coca-Cola do they produce in a day, in a year? That would be a ton of money. So they're always looking for these things to find maximums or minimums to optimize stuff. Okay? Now, application to calculus is if you can write a function for the cost, and your cost function looks like this. Well, right here, where the tangent is 0, you have a minimum. And then you can find that point and find out what the minimum cost is going to be. And that's going to be important. So what are we going to do? We're going to look for those maximum and minimums. We're going to find the derivative and set it equal to 0. And then we're going to use that to help solve our problem. Do you remember solving max-min problems in grade 11? We're going to do some of those same questions that you did back in grade 11 where you had to complete the square, and we're going to see how much easier calculus makes it. So here was one of the questions that you would have gotten in grade 11. You would have gotten an equation in this one. Y is the meters above the point where it's projected. There's a formula that was given, and you had to complete the square to find the vertex. What we're going to do now is calculate the time when the ball's at a maximum height. Instead of finding that vertex by completing the square, we're going to find that vertex using calculus. We can do that by finding the derivative, setting that derivative equal to 0, solving for t, and we find out that at 7.5 seconds, it's going to reach its maximum. If we wanted to find the exact coordinates We now know the x-coordinate is 7.5. We can plug that back into our original equation. And we find out that the maximum height is 56.25 meters. So, I mean, we're still using our calculator here to plug things back in, but maybe a little bit quicker than having to complete the square. Less work to show for sure. Do you remember these questions? Fred wants to enclose a rectangular parking lot. Because, you know, as soon as you make a parking lot, the first thing you want to do is make sure that you put a fence all the way around it. That's a good idea. Okay? Building on one side of the lot. So you don't need, so here we've got our building. Here's our building. We want a fence in this parking lot so nobody can get in. Good strategy. Keep that asphalt nice and new. And we want to use 60 meters of fencing to do that. Now, you could make a rectangular parking lot with 60 meters of fencing by putting 1 meter here, 1 meter here, and 58 meters here. That would not be a very good parking lot, only for really tiny, maybe just for motorcycles. If they could get into that fenced area, they could park there. But that wouldn't be a very good idea. What we want to do is we want to get the maximum area so that we're wasting as much space with this fenced parking lot as possible. Now, you can see that the area of this one's 58, right? And if I increased it 2 and 2, and then this would be 56, then your area is already up to 112, which is way more than 58. So the question is, what would be the best to do in this situation? Well, we have to introduce some variables. We don't know what the side lengths are, right? We could call this x and y, but our goal is to try and create an equation with just one variable. And what we want to maximize is we want to maximize the area, so we're wanting to create an equation for area with just one variable. So if I call this x, I would know this was x as well. And sometimes by doing a couple of numbers, you realize what you did. I put 1 and 1, and then how did I find 58? I just did 60, subtract those two 1s. And this one I did 60, subtract those two 2s. So here I got to do 60, subtract those two x's. And now I can create an area, because area is length times width, and that area formula that I created just has one variable. So again, what would you have to do if this was in grade 11? You'd have to multiply it out. So you'd have 60x minus 2x squared, and then complete the square. What happens with calculus? You find the derivative. You set your derivative equal to 0, and then solve for x. And you get x is equal to 15. So what are our dimensions? The dimensions are 15 by 30. Did it ask you what the max area? Find the maximum area with a maximum of 450 meters squared. Do you remember doing these ones? Did you do enough of them to realize a pattern? Did you ever find out that, oh, if it was 60 meters of fence, it was going to be 30 by 15. If it was 80, it's going to be 40 by 20. If If it was 100, it'd be 50 by 25, where you just halved it for one of the sides and the other side was a quarter. So the other nice thing about calculus is we could just say, in general, instead of 60 there, I just put some perimeter. I could make up any perimeter I wanted. Start with 120. Then this would be, take all my 60s out here. That's a little bit too small. Right? I put any perimeter in there, and solving for x is going to be my perimeter divided by 4. No matter what perimeter I put in, this x will always be a quarter of that. And so it explains why that pattern always happened. And then this one is always going to be half of that. And so your calculus can also find patterns like that and explain why those patterns always happen. So if you started with 120, 120 divided by 4, that would be 30 on this side, 30 on that side, and 60 on the other side. Here's one from grade 11. You remember doing this in grade 11 where you had a piece of cardboard, you cut out corners from that cardboard, which you could then fold along these sides and make a rectangular box with an open top. So you started with 10 centimeters by 7 centimeters. And it's an interesting thing because if you actually have like a piece of paper and you're trying to make a box, and this is something I do with my grade 11s when we do this unit, we have a competition. You feel bad when you're cutting out those squares. The bigger the square you cut out, the more material you waste. And so you feel like maybe I shouldn't waste any material. But if you don't waste any material, you just are still left with a flat piece of paper which has no volume. So you have to cut something out. So the question is, how much or how big should this square be right here in order to get that maximum area? Well, let's look at this box once it's made. Does it make sense that that x becomes your height? And that this length here, which was 10, now has 2 x's subtracted from it. And this length here that was 7 now has 2 x's subtracted from it. Since volume is length times width times height, we would have 10 minus 2x, 7 minus 2x, multiplied by x. So going back to grade 12, graphing polynomials and figuring this out, what do we know about this function? Well, it's in factored form. You would know that it has an x-intercept at 0, at 3.5, and at 5. You know that this makes an x-cubed graph. If you look at all of your x cubes, your x's, sorry, negative 2x times negative 2x times x, that will make a positive 4x cubed. A positive x cubed graph would go like this. And this would be a function of your x would be along here. This would be your y, which is your volume. So there we have a graph. We want to find our maximum volume. Well, looking at the graph, you might say, this doesn't have a maximum because my graph goes up forever. So I guess technically, according to this graph, it means that there is no maximum. You could take that piece of paper and you could make an open-ended box that would have a volume enough to fit the entire Earth into, right? We start to say, well, something can't be quite right here. Well, if we think about our actual situation, some things don't make sense. In fact, the only part that does make sense is this little section. Because as soon as you cut out a square bigger than 3.5 centimeters, if I cut out 4 centimeters, that whole 7 side is going to be gone. And then it no longer makes any sense. So if this is the only section that can make sense, we are looking for this point right there. So since this is a calculator question, one thing you could do is you could go to your graphing calculator and you could type in this equation and find that maximum. So if we go to y equals, clear out everything that we have, bracket 10 minus 2x, 7 minus 2x times x. And since I already know from my grade 12 graphing skills what this graph kind of looks like, I know that I'm only concerned from going from -1 maybe to 4 along my x-axis because it only makes sense between 0 and 3.5. And my y-min, I'm going to start at -1. And I don't know how high my volume is going to go right now, so I'm going to pick a number like 50. And then I'm going to hit graph and see if it even shows up. Okay, I happened to get really lucky with 50 that was a really nice part of the graph. So I'm seeing just this yellow part of my graph. Okay? I actually kind of hoped I would have a bad graph. So I'd be like, okay, I'm going to pretend again that, oh, I'm going to just pick 10 and see the maximum. And then be like, oh no, I can't see the maximum. Come on. Oh, there we go. So if this happened and you wanted to see some more, one of the things I wanted to show you is you can go above your graph button is table. If you go to your table and it starts at a bad number like -14, you can either like scroll. You can scroll until you get back to 0. Or above the window button, there's a table set button. What the table set button allows you to do is start at whatever number you wanted. So I don't know if you've ever done this or you've seen someone do it in class where they're like, the first time they see a table, they start going down to see how far down they can go. And then they're like at -3,000 or 3,000 or some big number. And then they're like, oh, I got to get back to 0. And I just let them, if they're going to do that, let them go all the way back up. And then when they get back to 0, I show them how to do this. So a table set at 0, and you can even say how much you want your table to go by. I still want it to go by 1. Now when I go to my table, it's starting at 0. And I can see between 0 and 4 what my numbers are looking like. You see I've got a 40 and a 36. So when I go to my window, well, since I see a 40 in there, maybe I'll make my y max. What might be a good number? Oh, maybe 50. And then our graph shows up much nicer. So without calculus, with a graphing calculator, it's very easy to go second, calculate. Number 4 is our maximum. We can find that maximum by going on the left side and the right side. Again, you can arrow over, or you can just use numbers. I know that 1 is to the left, so I type in 1, it automatically goes to 1. I know that 3 is to the right of it. And it's a little bit quicker than arrowing over. And then push enter again, and we find out that our maximum is at 1.35. So if you have a graphing calculator and you were asked to find a maximum, this for sure would be the fastest way to do it. But you have to know some things about your calculator, and you still had to know some things about sketching a graph so you could set your window and set your domain up so that it would be appropriate for the question. If you wanted to do this with calculus, it's not quite as easy, but it's still doable. So first of all, we would need to change this. I think it would make sense, rather than doing a product rule with our derivative, I'm going to multiply this out. 7x minus 2x squared. Distribute that x in one of them, and then multiply this out again. So when I multiply this all out, I'm going to get a 4x cubed. I'm going to get minus 20x squared, minus 14x squared, minus 34x squared, and plus 70x. And so now when I find my derivative, that is my derivative. Now, considering that's my derivative, and cheating a little bit by knowing that my answer is 1.35, I'm going to make the educated guess that you can't factor this. Because if it was factorable, one of the factors would have to be x minus 1.35, and that doesn't sound like a very nice number. So if you had to solve this by putting this equal to 0, and this was, if this was a non-calculator question, then the next point you would have to do would be to use your quadratic formula, negative b plus or minus the square root of b squared minus 4a. And again, now you have to know these formulas, over 2a. So negative b plus or minus the square root of b squared minus 4ac over 2a. So we get 68 plus or minus, I'm going to calculate that on my calculator, 68 squared minus 1264 over 24. And one of these, the subtracting one, will end up with a negative answer, which doesn't make sense because we know still that our answer has to be between 0 and 3.5. So when we add and do the positive one, whoa, maybe I made a mistake. Oh, we actually do have to subtract because the other one gives us, this one, right? So the first time I added, and I got 4.31, which was outside of what was reasonable between 0 and 3.5. So now I am going to subtract. And I get the exact same number that we got from our calculator. So in this case, the graphing calculator is still quicker and more efficient if you know how to set up your window and how to solve for it. But you could show all of your work with calculus as well. So in this right-angled triangle ABC, AB and BC can change, but their sum is always going to be 6 centimeters. So if the length of A to B is x centimeters, how long is it from B to C? in terms of x. So this one, I want you to do this first part. I want you to do B and C as well. Put up the answers in a second. So if those two sides always add up to 6. The other side would be 6 minus x. And then, if you wanted to find the maximum area, well, area is base times height divided by 2. 1/2 of x, negative 1/2 of x squared plus 3x. Once you distribute that and divide by 2. I mean, you could write it as 6x minus x squared divided by 2, and that's 3x. That would work out as well. It means the same thing. And now to find our maximum area, we take our derivative. Well, our derivative is that 2 would come out in front, making it just minus x plus 3. Set that equal to 0. And you get x is equal to 3. So the one side's 3. The other side then would be 3 as well. That would give you a maximum area of base times height divided by 2. 4.5, was it centimeters? Did it give a unit? Unit squared. Perfect. Centimeters squared. That doesn't look like a centimeters at all, actually. Kind of C. This is little c. This is the m here. Okay, yeah. All right. Now it looks like EM squared. Okay, super fun question. Now, the numbers that I have here are numbers so that things work out nicely. But what I'd like to do at the same time is sort of think about it with other numbers as well. We've got a right circular cylinder. In other words, we should draw this with a dotted line. So we've got a right circular cylinder that has a radius of r and a height of h and a volume of 54 pi centimeters cubed, right? When was the last time you bought a canned drink that was close to having 54 pi milliliters in it? Huh, right? The number doesn't ring a bell, does it? That's because they don't do that, at least not yet. Maybe they should. Maybe people would learn math better if instead of writing 355 mils, they would do 1.1 pi or something like that, so that you'd have to do some math, or 110 pi to make it close to 355 or 120 pi or whatever it was that would be the closest. But no, they don't do that. They actually write 355. So I'm going to imagine here, instead of 54 pi, we're going to solve it with 54 pi because it's going to have nicer numbers. But we could do this same question with 355 centimeters cubed. Everybody knows that 1 centimeter cubed is the equivalent, if it was water, to 1 mil. And so that's why when you get a needle at the sometimes they say what you need 10 cc's. Have you ever heard that language? And that cc stands for cubic centimeters, but it's actually milliliters of whatever drug that they're putting into your arm or vaccine. So what we want to do here is we want to think about our cylinder, and we know what the volume needs to be, and we're going to show that the total surface area of this cylinder can be this formula. And then what we're going to do with this equation is then find out what dimensions should we have for our radius and our height so we have a minimum surface area? And this is one of these questions that like I said, it's one of my top 3 math questions of all math courses of all time, that it is awesome to solve because we can see a real life application. You are working for a soft drink company. You need to make cans to put soft drinks into. They are roughly right cylinders, okay? What should our size of our can be so we can minimize the surface area? Because if we use less aluminum, it's going to cost us less, right? If we made, like, can you imagine really, really flat cans that were really big and really wide that had 355 mils, and you had to basically hold them like that to drink it all? It would use a lot of aluminum and wouldn't be very efficient. And then it would cost you more to ship, and it would cost you more to buy the aluminum, and probably cost you more to make, and it wouldn't be very smart. It would be cool, just like at Christmas when they have like the ornament ones. Anyways, okay, so we want to show that the surface area, well, if we start off with our surface area, you have to know some surface area formulas. Do you remember your surface area of a cylinder formula? Say no. You kind of remember? If you can visualize it, your surface area, can you see that there's 2 circles? One on the top and one on the bottom. So let's start off with 2 pi r squareds, because those are 2 circles. Now we need to figure out the surface area around the cylinder, okay? And what I suggest to help you figure that out is go home to, if you've got canned soup in a cupboard at home, just take off 5 or 6 labels until you figure out what the shape of each of the labels are. Don't tell your parents, just throw the labels away. Have you ever taken a label off a soup can? What shape does it make? A star. A balloon. Right, so here's, right, if this was the label on this cylinder and I pulled it off, I get a rectangle. And so what do we know about that rectangle? That rectangle that gets pulled off, this is the height. How long is this part? That's your circumference. And so, without having to memorize the formula, if you can visualize it, you're going to have 2 pi r, which is your circumference, times by your height, and that's going to be our total surface area. Now, the problem with our surface area formula, like we have it right here, is that it's got 2 variables. It's got a radius in it and a height in it. And that's why this question says, show that it's equal to this, and that equation there only has radiuses. So what we're going to need to do is we're going to need to get rid of that height. And the way that we can do that is we were told something about the volume. How do you find the area or the volume of a cylinder? Again, anything that is the same shape going all the way up, you just have to find the area of the bottom. In this case, it's a circle. And if you keep imagining adding areas of circles and stacking them and stacking them and stacking them all the way up, you'll fill up the whole thing, and that'll be your volume. And so all your volume is your area of your circle times by your height. And since we know our volume with the nicer numbers is 54 pi, well, one circle on the bottom is pi r squared. And we have 2 circles. Yeah. So when we know our volume, and if you were actually figuring out your can of Coke, this is where you'd put 355 there. Have to use Coke. We're not allowed to use Pepsi after the commercial. To solve for h, you would have to divide by pi r squared. Well, that's how much an actual can has, right? 355 milliliters? So I'm just saying, as a thought experiment, if you wanted to think about using this with 355, you would do that, you would write that number instead of here. But everything else would be the same. But we're going to use our numbers here. I'm going to simplify this. I get 54 over r squared, and that's what's equal to h. And so now my surface area formula I have that 2 pi r times h, but instead of h, I can write 54 over r squared plus the 2 pi r squared. And if I simplify this, one of these r's is going to cancel out, and my surface area is 108 pi over r plus 2 pi r squared. Now, our whole purpose of doing that was to get a surface area equation with just one variable. Because now that we have a surface area equation with just one variable, we can find the derivative and then find the minimum surface area possible. So what does that look like? Our surface area was 108 pi divided by r. Are you okay if I make that r to the minus 1? Plus 2 pi r squared. So our surface area derivative will be a negative 108 pi r to the negative 2 plus 4 pi r. Set that equal to 0. I'm going to put that r squared back on the bottom. If I want to get rid of that r squared on the bottom, I can multiply both sides by r squared. And this is why we had the numbers that we did. When I divide by 4 pi, I get 27. And then the cube root of 27 is 3. Nice numbers. So that means our radius is 3. Remember that our height was equal to 54. Here, let's go back up. Our height was 54 over r squared. So our height will be 54 over 3 squared, which is 9. So our height is 6. Again, nice numbers. So the question said, find the radius and height which makes the surface area a minimum. The radius is 3 centimeters. The height is 6 centimeters. Of course, if we use 355, we wouldn't get nice numbers. Right? They'd be decimals. We'd have to use our calculator more. But it would be interesting to check how close are the dimensions of a Coke can to those dimensions. How did they have to change things? Because I mean, it's bowed at the bottom for strength, and the way that the lid is made. So they have to take into consideration how much aluminum is made there. But I would guarantee that they've thought about minimizing how much aluminum they have to use to make that can, and then having the best possible. Now, to create the most volume with the least amount of surface area possible, the best shape to do that is a perfect sphere. But I think for practical reasons, they haven't made drink containers in perfect spheres yet. Right? Probably a little bit problematic on any kind of surface that's not quite flat. There goes your drink. Spilled it again. And so the cylinder seems to make sense. I think the cylinder is also good because it has that, but when you pack it together, you're still not wasting a lot of space.